Alright, we're going to conclude section 14.8 in this video, and we are on page 968. We're going to do number 21. In exercises 18 through 25, evaluate the integral by a suitable change of variables. So in the previous lecture videos, we've done a couple of problems where we were not given the change of variables, which is like this problem that we're going to do now, and we've done a couple of problems where we were given the change of variables. So here we're evaluating the double integral over region R of x squared dA, where R is the region bounded by the ellipse x squared over a squared plus y squared over b squared equals 1. So for when we were given our change of variables, for one problem I sketched the region, one problem I didn't. I'm going to sketch this region just to talk about our general approach. We don't really need the sketch, but I just want to give a recap of our general approach so we can then look at how this problem differs from some of the other problems we've done. So they gave us an equation of an ellipse. And it said x squared plus y squared. X squared over a squared plus y squared over b squared equals 1. All right, so x squared over a squared plus y squared over b squared equals 1. So this will be our region R. So this region actually is both the type 1 and the type 2 region. So we could try to directly evaluate this integral, but that's not what our directions told us to do. They told us to actually do a change of variables to do it. So in the past, when we had to figure out our change of variables ourselves, we were fairly easily able to figure it out from our region or our integrand. So in the past, like our region may have been something like some kind of parallelogram where we had, I think in one problem, we had two lines were of the form x minus y equals a constant, and then the other two lines were of the form x plus y equals a constant. So a natural transformation would be to choose u equals x minus y and v equals x plus y. Here we could, like, say, solve for x and get the top half solve for y and get the top half and the bottom half of this ellipse, but that still wouldn't give us a transformation. That would be us approaching it as though we're doing this problem directly. So we don't see those equations, like 4 equations of a line or something swimming around in here to easily give us an idea, or 3 equations just swimming around, nor do we see something in our integrand. So in some of those problems as well, the equations, the expressions we saw in our integrand would be similar to some of the expressions that we would see in our picture when we sketched our picture. So we don't have any of that here. But what we'll use is our knowledge of regions over which we know how to integrate functions of two variables. So if it were, say, a square, we know how to do that. A rectangle, we know how to do that. A triangle, so type 1 and type 2 regions. So that's oftentimes what we've been looking at. We take this and we transform it in a type 1 or type 2 region, and then we go from there. But an ellipse is closer to a different type of region that we covered. That's not where we didn't look at it as type 1 or type 2, where we cover polar regions. So if we have an ellipse, maybe our transformation instead will be some transformation where we can turn this ellipse, instead of trying to turn it into a rectangle, turn it into, or a triangle or something like that, which is what we did for all of our other problems. Let's see if we can turn this into a circle instead. So if our transformation can turn this into a circle, then we know how to evaluate integrals over circles because we're familiar with polar coordinates. So it's fairly easy to take this and transform that into a circle, because we have x over a quantity squared plus y over b quantity squared equals 1. So if we just let u be equal to x over a and v be equal to y over b, then we end up with u squared plus v squared equals 1. That's exactly what that says with this transformation. And now in the UV plane, we have a circle of radius 1 centered at the origin, and we're very familiar. This is our boundary. So that's what we've been doing for all of these regions, is we find the boundary of the region S in terms of U and V, and then we just shade that region S in. Same thing here. We find the boundary of the region S in terms of U and V, and it so happens this is a circle, and we want something that over which we know how to easily integrate. So now in the UV plane, we get a circle of radius 1 centered at the origin. So that's S right there. So now with this, we now want to integrate over this region, and we still don't explicitly have any bounds. We don't have what U varies between. We don't have what V varies between. We could here do this as a type 1 or type 2 region and say, okay, we could solve this equation for V and get the top half of the circle and the bottom half of the circle, and then say U goes from constant to constant from -1 to 1. So we could do that and treat this as a type 1 region. But before we dive into doing that, let's just do the remaining steps of the problem, and then we'll go from there. So this was step 2 right here. So we don't have our bounds for U and V yet, but we're not too concerned about that because we know how to set up bounds for a circle centered at the origin. All right, step 3. Step 3 is we need to take these equations that we have here, and we need to solve for x and y. So now, if you try to avoid that and say, okay, well, I'm going to use the reciprocal approach for the Jacobian so that I don't have to solve these. I mean, of course, these are easy to solve for x and y. But if you say, okay, well, I'm going to try to avoid that, you're going to end up running into an issue anyway because there's an x up here anyway. So you need to know what x is equal to in terms of this. So, but these are, of course, very easy to solve for x and y. So x is equal to AU, and y is equal to BV. All right, so now we've solved those. Now we're ready to find our Jacobian. And we don't have to use the reciprocal approach. We can just find directly from these two. So for the Jacobian is equal to the partial of x with respect to u, which is a, and then the partial of x with respect to v, which is 0, and the partial of y with respect to u, which is 0, and the partial of y with respect to v, which is b. So we just end up with, and we'll just end up with a times b, and I'll address that later. I was just going to talk about whether I need to use the absolute value or not in the integral, but I'm not in the integral yet, so we don't need to address that right now. All right, so now we want to set up our integral. So we still don't have any bounds, but we know our region over which we're integrating is S. So we'll just write it as the double integral over S of our integrand. Our integrand was x squared, so x squared is just a squared times u squared. So a squared times u squared, and then times the absolute value of our Jacobian. So we can assume that we took a and b to be positive here. So you don't need to put the absolute value on there because all we were doing was we chose this transformation ourselves. So we can choose it, or we can specify our a and b are greater than 0 on there. Or you can say they were both less than 0 and put the absolute value. Or even in that say, if they're both less than 0, you don't need the absolute value there in that scenario either. If you chose them with opposite signs, that's the only scenario you would need the absolute value. So we still need AB in our integrand. And then that's DA because we don't have any bounds on S. So now what you do is you look at this problem So you don't want to forget any of your integration techniques, or nor do you want to forget any of your setup approaches that you've learned in previous sections. If we weren't in 14.8 and you were given this integral right here, and you know that a and b are just constants, so actually let's pull those out so to eliminate some confusion. So we end up a cubed times b double integral over s of u squared dA. So now, if you were not in 14.8 and you just were given this is the region over which you want to integrate and this is your integral, what would your natural approach be? Okay, you see that thing's a circle, so you would say, okay, well, I want to do this in polar coordinates. Now, don't get hung up on the fact that we have u and v here. Polar coordinates can be done regardless. X and y, we use them all the time, but they're dummy variables. It doesn't matter. We could use u and v to set up our coordinate system. We could use whatever we want to set up our coordinate system. So we're going to look at this the same way we would look at polar coordinates if it were x and y, but now it's u and v instead. So now the polar coordinate transformation, which would be our natural approach if we were to encounter this integral, the polar coordinate transformation, instead of x equals r cosine theta, would be u equals r cosine theta. And then instead of y equals r sine theta, it would be v equals r sine theta. So in polar coordinates, u equals r cosine theta, v equals r sine theta. And there's also nothing restricting you from just saying, you know what, I'm just going to do this in rectangular coordinates and I'm going to solve for v here and approach it that way. Like, there's nothing wrong with that. It's just I wanted to show you that you can still just use whatever your natural approach would be once you finish doing your change of variables. And we could write that u squared plus v squared equals r squared, but we really don't need all that. All we need, is that we see that r varies from 0. Well, I guess I should label this as 1. There's a 1 right there. That r varies from 0 to 1, and theta varies from 0 to 2 pi. So S is a set of points r comma theta such that r varies from 0 to 1, and then theta varies from 0 to 2 pi. I guess I should have written that the other way because we normally put the thetas first, but it doesn't matter. So now our integral over S, becomes the iterated integral where theta varies from 0 to 2 pi, r varies from 0 to 1. Oops, I forgot about my a cubed b, so let's put that somewhere. A cubed b. And then u squared is r squared cosine squared theta. R squared cosine squared theta. Whenever we set up an integral in polar coordinates, we have that additional factor r in the integrand. So that's that r that comes from polar coordinates. And then these were r's, so that's dr. And those are thetas, d theta. All right, so just because we've already done a change of variables doesn't mean we can't do another change of variables. So we had done the change of variables that got us to this point, and then the easiest way to evaluate that integral was to just do it in polar coordinates, which is another change of variable. And that right there, that factor r that we see in polar coordinates, that is the Jacobian for the change of variables from rectangular to polar. The factor r that we see in cylindrical coordinates is the Jacobian. The factor rho squared sine phi that we see in spherical coordinates is the Jacobian. So we've done change of variables in 3 sections already. We just didn't go into as much detail. So what I'll do in the last few minutes is just go over kind of relating what we've done graphically in previous sections with regards to polar cylindrical and spherical coordinates to what we're doing in this section. I won't go through all the details, but just so you have an idea of what aspects were kind of missing in the background and why those approaches work. So say for instance, I'm just going to make up the region R, and we're going to do an easy region R. So let's say our region R. This is completely independent of that last problem that we did. So in the XY plane, so we have a circle of whatever, radius 1, centered at the origin. And this is our region R. Given by x squared plus y squared equals 1. So what we do, depending on our integral, of course, oftentimes we opt to do this in polar coordinates. So in polar coordinates, this is theta varies between 0 and 2 pi, and r varies between 0 and 1. Now, what we did in section, and I didn't write out what the relationship between x and r, x, r, and theta, and y and r and theta are. We're given that in polar coordinates. Only thing I want to point out is that when we were doing polar coordinates, we never sketched our region in the r theta plane. But notice if we did, and this is why things are easier when you switch, is because if we sketch this in the r theta plane, r varies from 0 to 1, so from 0 out to 1, and theta varies from 0 out to 2 pi. Oops, that's the r theta plane. This thing in the r theta plane, this is the new region S, which is just a rectangle. So that's why we go through and do that. And that's what we were seeing happening in 14.8 is we were saying, okay, we had this region in the XY plane. We set up some transformation. I didn't write the transformation. It gives us some bounds. And then we sketch the region in the, whatever the new variables are, r theta, with the bounds that we got. And now we have a simpler region. We have a rectangle. So similarly, we would see, say, for instance, we were working in, we're working in spherical coordinates. Not spherical, let's do cylindrical. We were working in cylindrical coordinates. And we had the region D, over which we wanted to integrate was, I'll just use a cylinder to make our lives easy. Now, of course, in polar coordinates, we don't have to be integrating over it. The region doesn't have to be a circle. It could have been a quarter circle. It could have been a bunch of different things. So actually, we'll do that for this. We'll make this, instead of a full cylinder, let's make it a quarter of a cylinder. So we're just going to ignore that part of my picture, just so I'm not doing the same thing over and over again. Let's make this a quarter of a cylinder. And let's say it goes from, this is whatever z equals 2 down to z equals let's say down here this is z equals -1. And let's say the radius on this cylinder is let's say the radius is 3. So this out here is, this is x equals 3. All right, so now in cylindrical coordinates, if we were to look at this, we would say, okay, well, z goes from -1 to 2. We see that. What do theta and r vary between? So this would be our region D. So we would actually have this region shaded in, but I don't want to shade it in, so we don't get, well, I guess I could just shade it in like this. So that's our region D. So if we were to look at this in cylindrical coordinates, we would say, okay, well, r varies from 0 to 3. Theta varies from 0 to pi over 2. So theta goes from 0 to pi over 2. R goes from 0 to 3. And Z goes from -1 up to 2. And then if we were to sketch this, this is in X, Y, Z coordinate system. Now if we take this and we sketch it in, instead, we sketch it in the R theta Z coordinate system. So we're going to sketch that in R theta Z. So let's do this R theta Z. So if we sketch this here, then theta goes from this number to that number, and we're on the theta axis. So we're going to go from 0 out to pi over 2. R goes from 0 out to 3. And then Z goes from -1 to 2. So let's say -1 up to 2. And what we would get there is we would just end up getting a box. So we would get something that looks like this. So that will be our region S, which notice this region is a lot simpler than that region is right there. So that's the same thing that we've been doing in all of those. We've been doing the same thing in those previous sections that we were doing in this section 14.8. We just never sketched this region. And you can do the same thing with spherical coordinates. If say for instance you were given a hemisphere or some portion of a sphere, it doesn't matter. And it doesn't have to be a cylinder or a circle or a sphere. It's just whatever you're using in spherical coordinates. So let's do the ice cream. Let's look at the ice cream cone in spherical coordinates. So X, Y. And you don't need to know how to do this for 14.2, 5, and 6, but this is what we're doing in 14.8, so it may be useful to just know this for 14.8. Say we had the ice cream cone problem, and we were doing it in spherical coordinates, and I'm just going to say that here our we know our theta here varies from 0 to 2 pi because we're going all the way around. We'll have our phi go from 0 out to pi over 4. So let's say theta goes from, we can see theta goes from 0 to 2 pi for that. Our phi goes from the positive z axis all the way down to pi over 4. And we'll have we'll say our rho went from 0 out to whatever. Let's do a sphere of radius 2. So rho goes from 0 out to, let's say, out to 2. All right, so that is what that would look like in spherical coordinates. Now, if we were to sketch this though, in the XYZ coordinate system of spherical coordinates, these are the spherical coordinates, but it's sketched in the XYZ plane. If we take it and we sketch in the rho phi theta plane, it's going to look like this basically, just a different size. So, not plane, coordinate system. Sorry, I said plane. So, rho phi theta. Rho goes from 0 to 2. Phi goes from 0 to pi over 4. I mean, I'm not trying very hard to draw these in any kind of scale. And we would just end up again with this rectangular. So we end up with something like that. So this was the region D. It turns into this region S, which is why switching to spherical makes things easier than working in rectangular. Same thing here, switching to cylindrical makes things easier. All right, so these transformations are what we're doing in 14.8 in general. I didn't write out any of the transformations. I just wrote out the bounds, but you all know what the transformations are. If you want to know how to go from rectangular to here, or if you want to know how to go from, like, say, rectangular to polar. All right, so I'll stop this video here, and then on our next video, we'll begin section 14.9.